Welcome to this third lecture video for Physics 4A. In the lectures in this video, we will work through a couple representative examples of kinematics problem solving. We will also introduce the key concepts and problem-solving approaches applicable to projectile motion, a type of two-dimensional motion under constant acceleration along one axis. We will look at a standard projectile motion problem first. And then, using the same tools, we will look at a couple fun examples. One involving a launcher that is mounted on a cart which will be sliding down an incline. And a second past midterm exam question in which connecting the given information to the unknown being asked for is tricky. With all these examples, this video is a bit longer than usual. Do please make sure to at least watch it through the standard projectile motion problem example. One aspect of two-dimensional kinematics that we are not covering in detail right now is the uniform circular motion, in which an object moves along a circle at a constant speed, but not constant velocity. Because moving along a circle always involves an acceleration, which causes the direction of the velocity to change. We will come back to this setup later, after having covered the forces and problem-solving approaches using force analysis, where we use the fact that the net force will be equal to the centripetal, that is, center-seeking force in situations like these. For homework questions you may have to answer this week, following two things should be enough information. 1. Things moving along a circle at a constant speed are undergoing an acceleration, as we define it in physics. And 2. This acceleration, called centripetal acceleration, is given by the formula that acceleration is equal to speed squared divided by radius of the circular trajectory, the boxed formula on the screen. Hi, this video is a problem-solving example for 1D kinematics. So this is one of your homework questions. I'll demonstrate solving this problem just from the beginning to the end. When you work on the question, do look at the hints and try working it out for yourself after having watched this video. Okay, so the question says, a diver bounces straight up from a diving board, avoiding the diving board on the way down, and falls feet first into a pool. She starts with a velocity of some number of meters per second. By the way, your number will be different, it's randomized. And her takeoff point is some number meter above the pool. Note use g equals 9.8 meter per second squared throughout and report all answers to two significant digits. Okay, so that's the setup, and the question actually asks, what's the highest point, how long is she in the air, and so on. But from the information given in the problem itself, I can start drawing diagram, and I highly recommend that you get into habit of, as you are reading the question, just diagramming the information that's being given by the question. It's a way to kind of recap for yourself what information is given, and if you are missing anything, it's a kind of an intuition you have to develop, so it takes practice. Alright, so I have a diving board here. The drawing doesn't need to be very artistic, and mine are not. And our diver is going to jump upward with some speed v0. And I was given the number of 3.75 meters per second. And you have the description of diver's trajectory. She moves straight up and then straight down, missing the diving board and then striking the water. And I was given the distance between the diving board and the water, let me call that height, h, of 1.8 meters. Oh, and let me highlight this as a reminder. G equals 9.8 meters per second squared. All right. So once you have this all diagrammed out, what I would recommend is pause for a bit, look at the information that's given to you, and see if just feel your way to if it feels like you are given complete set of information. If you knew that someone was jumping straight up at some speed, does it feel like you have all the information you need to know how high the person will go? Maybe. Um, and do you feel like you have all the information you need for how long the person will be in the air before striking the water surface? And how fast she'll be going? When you're starting out, you might not quite have that feeling yet. Maybe I think a part A is a little bit easier because you know how fast something is going, how high it reaches. It's probably one-to-one relationship. You don't have any other variable you need to worry about. So I think that is more doable. The rest, until you have done some kinematics problems, it can be hard to know when you have complete set of information. But I recommend that you get into this practice because the first step in solving problems is first feeling like you can solve them, knowing in your heart that you have information to solve them. So let's go right through here. We are looking for the highest point. So let me walk you down a few false steps first. So you look at the highest point, so you might be thinking, oh, position. So which of my kinematics equations involve position? Let me write those down. I have this one that says height or y position is equal to minus 1/2 gt squared plus initial velocity y times t plus initial height. Why not? Well, y, 0. And before you go too far with this step, you have to do a little self-check to make sure that you don't waste any time. It's the check of, do I have all the information I need? Do I have initial y position? Oh, I think I do. I need to decide on where I'm going to say y is equal to 0. I'm going to say my y is equal to 0 at the water surface. You don't have to, but that choice seems natural to me here. So my initial height is going to be h. I have that. I have my initial velocity. I'm going to call it v naught. I have g. And I'm looking for the height or the y position at the highest point. So I don't actually know y. And the reason we are going through this exercise to see if we know every symbol here is because of this. This is a general rule in algebra. You can only solve for as many unknowns as there are equations. I hope that sounds familiar. I don't know where I learned it, but I learned it in one of my math classes, probably algebra. So, because we already have one unknown here, that means we have to know every other variable. So we know y naught, we know v naught, we know g, all those are fine. But here's your trouble. I don't know time t. So if you're trying to use this equation to solve this problem in one shot, you can't. You have too many unknowns. All right. So you have two options here, and you can go either way. For those of you who might be more experienced in problem solving, you might look through your kinematics equations and realize you can use the v squared formula. If you realize that, great, do it. You'll do fine. Let me go the other way. I'm going to actually continue using this equation that I picked first because it's a good equation. It's useful in a lot of circumstances. And I have a feeling I'm going to be using it for part B. So what I'm going to do is I'm going to instead try to find t. So the Only problem with this approach here is that we don't have as many equations as we have unknowns. So I need one more equation that doesn't introduce any more unknown to bring the balance to my number of equations and number of unknowns. So I'm going to keep this equation. Let me call it equation 1. So I have some way to refer to it. And I go through the rest of the kinematics equations in my head, or I might have a cheat sheet, well, in my head. So I'm looking for something that involves time. That's not the v squared formula. It explicitly doesn't have time. But I have other equations that involves velocity. So this is the equation that involves velocity. The velocity v is equal to initial velocity and plus acceleration times time. That's why I'm bringing it up. Here the acceleration is minus g, so minus gt. All right, this looks promising. I don't have any new unknowns because the v naught here is the same v naught, g here is the same g I was using before, and time, that's unknown, but it's the same unknown. Here's a problem. What's v? Because that's different from initial velocity v naught. So you need to know the velocity at the highest point. And this is the place where I see many students get stuck. And this is the place where the practice of diagramming the situation and developing a physical intuition will help you long term, now and down the road. Because if you think about this situation carefully, you actually know this information. You might remember it from your calculus class too. So what I like to do is I like to visualize. I like to imagine actually watching a diver who jumps up, who reaches the highest point and then drops down. At the highest point, how quickly is the diver moving? And after you think about it for a while, I hope you realize at the highest point, the diver isn't moving. It's the point where the diver is neither moving up nor moving down. So you know this answer already. It's 0. And in a way, the problem was giving you that information by saying the word highest point. But to make use of that information, you have to have a good mental picture of the situation. So okay, we have 2 equations and only 2 unknowns, the time t and the position y. So now the rest is a matter of algebra. So let me do that. I'm going to solve equation 2 for time. That'll get you t is equal to v naught minus v, but that was 0, divided by g. So v naught divided by g. And so this is the technique that you remember hopefully as a substitution. That's why I solved for t. That gives me a tool that I can use to get rid of t's in the other equation. So we plug this into 1. That gives me this single equation. Y is equal to minus 1/2 g v naught over g squared plus v naught times v naught over g plus h, which has no unknowns other than y. So we have solved for y. So simplifying a little bit here, the first and the second terms get combined to get you v naught squared over 2g plus, and the third term, h. Alright, I think this is as simple as I can get. So now I'm ready to plug in the numbers. The v naught is 3.75, g is 9.8, and h is 1.8. And as a double check, you should work out the units and make sure that you get a unit of meter. So let me do that on the side with the calculator. And I get the answer of 2.52 meters. But if you plug this in, you'll find that you the system says it's wrong. That's because you need to read the question carefully. Above the board. So they don't want the y position. For one, they don't know where I set y equals 0. So since I know the board is at 1.8 meters above, now I had to subtract it out of here, 2.52, to get the actual answer that they're looking for. So let me do that. And the answer to part A is 2.52 minus 1.8, or 0.72 meters. So that's how high above the board the diver reaches. All right, part B. How long a time are her feet in the air? Okay, that feels like it's something I can answer with one of the equations I've had before. In fact, going back to equation 1, so we are looking for time. So here it's okay that time is unknown since I'm looking for it. And how long a time are her feet in the air? Let me rephrase that a little bit. So rephrasing, what they are really asking is, at what time does her feet hit the water? Oh wait, not does, do her feet hit the water? Does that rephrasing sound right? Okay, that makes it easier to say what I want to say about y. Not y, but the letter y. So at the time when her feet hit the water, what is the value of y? I said y equals 0 here. So y is 0 when her feet hit the water. Okay, then I know the value of y. It looks like equation 1 will just work fine. Let me write down the rewritten version of equation 1 for solving part B. So let me call this 1b. 0 is equal to minus 1/2 gt squared plus v naught t plus, I'm going to plug in the symbols I'm going to be using, h. Alright, t is the unknown. I'm going to have to use quadratic formula. Many times in constant acceleration kinematics problems, sometimes it turns out that you have to use quadratic formula. I try to avoid it as much as possible, but sometimes you just have to. So let me do that. Hopefully you have it all memorized. So this is already in that form of A, B, C. So let me just write it out. So according to quadratic formula, t is equal to minus b. So that's minus v naught plus minus square root of b squared. So that's v naught squared minus 4 times a, capital A. So that's the coefficient minus 1/2 gt. So let me use that minus to cancel out this minus. So minus g over 2, that's a, quote unquote, times c, that's the constant h. So that's under the square root divided by 2a. So it's minus 1/2 g times 2, so minus g. Alright, you can simplify it a little bit, but not too much. That's equal to v naught over g, and if I'm being picky, minus plus square root of v naught squared over g squared plus, let's see, 2 cancels out 1 factor from 4, 1 factor of g cancels out g, so it should be 2h over g, square rooted. Alright, as I said, doesn't simplify that much. So you have to plug in the numbers. Let me do that off on the side with the calculator. Oh, you get 2 answers, right? So with the minus sign, you get minus 0.33 seconds. And with the plus sign, you get plus 1.10 seconds. And here it's probably clear enough that the answer you should pick is the plus 1.13 seconds, because the minus sign, it It's unclear what that even means. But you should get into a habit of kind of trying to make a sense of even the answers that you are going to be discarding. And this is what that negative answer means. So this equation that we used, equation 1, it covers beyond the trajectories we are considering. So we are right now only considering from t equals 0, going up, then down. But it actually describes the motion for all time. So you have this hypothetical part of the trajectory where the diver comes out of the water at some speed, goes up, and at time equals 0 reaches this spot. And what that minus 0.33 seconds reflects is this moment in time here, the hypothetical moment in time when the diver could have come out of water with enough speed so that she reaches this point on the diving board at time equals 0, and she continues the rest of the actual track. And all that's hypothetical. It didn't actually happen. So the correct answer is 1.10 second for part B. All right, let me clear some of the board space for part C. What is her velocity when her feet hit the water? What is her velocity? It feels like this equation 2 is still relevant for the question. So we are looking for velocity. Good, we don't know that. V naught we know, minus g we know, and time. Oh, that was part B. So we have that answer right here. We can plug that in and we can get an answer. So let's do that. V is equal to V naught minus g times the time. This time I'll just write out the numbers. 1.10 seconds is equal to, let me plug in the numbers in the calculator. So it's minus 7.03, and it should be meters per second. You should work out the units for yourself. Make sure you didn't make a unit mistake. And it says 1 decimal place, so equal to minus 7.0 meters per second. Why is it negative? Oh, right. Upward direction is positive. So when the diver hits the water, she's going downward, so her velocity should be negative. Now there's a bit of an ambiguity here. Does the system want you to answer a negative answer or a positive answer? So this is where you read it carefully. It says velocity. So I'm going to assume that they wanted me to indicate direction along with the speed. If they wanted a positive answer, then they would have said the speed. The ambiguity here is that what if you defined it downward as positive? Because nowhere the question is specified. But upward as being positive is such a common situation. That's what it normally would be. So I would try plugging in minus 7 meters per second first. And here I tried it. It turns out to be correct. Now, if it isn't correct, then to get the correct answer, you should try plus 7. And I would actually report it as an errata, because something like minus 7.0 meters per second is not accepted as correct. Then there's enough of a room for misunderstanding and ambiguity here that the question should be corrected. All right, so that's a part C, and I guess that's everything. So this was a long problem. Hopefully you got something out of it, and try your handed problem solving on the remainder of the homework, and email me if there are any questions. In this video, we're covering projectile motion. Projectile motion is covered in section 4.3 of your textbook, which gives you an example of projectile motion. I think you had a reading assignment about that. And the textbook does go on to derive a few formulas. And I think sometimes mistake a student can make is look at these formulas derived the time of flight, like trajectory and range. And some students can get hyper focused on these numbered formulas, thinking that that's what you have to memorize, that's what you have to learn. And nothing could be farther from the actual approach in physics. So in this video, what I want to do is I want to show you the derivation of the formula. Not to show you the derivation of formula because you can read that from the textbook, but to demonstrate the kind of flexibility that you gain by being able to derive the formulas from the first principles yourself, rather than memorizing this final result that someone else has done. If you know how to do this yourself, then when someone tweaks the situation a little bit or changes something, you can do it yourself. And that's really the power of the problem-solving approach in physics. So let me take some amount of time showing you that. So this is a kind of a standard setup for projectile problems, where you have a projectile that is launched in a direction at some angle, theta from horizontal, with an initial speed of v0. And in the standard setup, this happens on a level ground. So the projectile follows some trajectory and lands. And there are some common things we can ask about this setup. We can ask, what is the range? R. We can ask, what is the highest height reached by the projectile? Or you can ask, at what time does the projectile land? Those aren't the only types of questions you can ask, and that's the first flexibility you gain. By being able to analyze the entire situation, you can answer no matter what aspect of the situation someone asks. You don't need to have a set formula for that. If you have a framework for analyzing the whole thing, then you just look at that part that you have worked out. So for our example, let me label these A, B, and C and answer these questions. So the first thing you have to do is break down motion into components, into the horizontal and vertical components. And you start on that by breaking the initial velocity into horizontal and vertical components of the velocity. So this here is the representation of the velocity vector, and it has horizontal component and the vertical component. And the vector is at angle theta from the horizontal component. So it feels a little bit silly reminding you of this, but here you use SOHCAHTOA to figure out the expressions for these components. You know, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. I mention this because sometimes students make mistakes swapping sine and cosine, and a lot of that comes from I don't want to call it laziness, automatic habit. So let me show you a way to avoid that. So the way to avoid that is to draw the triangle as I've done here, and use these trig relationships to write out that relationship. So looking at the y component of the velocity, it's the opposite side. So given the angle and the hypotenuse, I can relate it to those with the sine is opposite over hypotenuse, or rearranging that, the opposite side, v or y, is equal to the hypotenuse, v0, times the sine of theta. And the x component is the adjacent side, so v0 x is equal to the hypotenuse, v0, times the cosine theta from ka. Now, what I mean by automatic habit is, frankly, you are going to see expressions like this a lot. And sometimes people get into habit of thinking that that's always going to be the case. And I just want to caution you, it depends on the situation. Sometimes you will see cosine associated with the y component. sometimes you will see sine associated with the x component. And the way to avoid a mistake is do what I did here. Draw the triangle and work out the trig relationship. Alright, now that you have broken the velocity into horizontal and vertical components, what you first have to remember for projectile motions is that the horizontal and the vertical motions are independent. What that means is you figure out the acceleration that applies to each component and you write out what looks like a 1D kinematics equation for each of those components. So the acceleration along the x direction or horizontal direction is easier. It's 0. So the horizontal kinematics equations will appear simpler. And the acceleration along the y direction, let's say the upward is positive. So it'll be minus g. Alright, let me write down the x component first. It's easier. The x position is equal to the initial x velocity, v naught cosine theta times time plus, the initial x position. I need to define my axis and I'll say x is 0 where the projectile starts. That makes things easier. So that's it. Because the acceleration is 0, the kinematic equation is simpler. Now let's do the vertical component. The y position is equal to 1/2 times the acceleration, which is minus g. So minus 1/2 g t squared plus the initial y velocity, v naught sine theta times t plus the initial y position. I guess I should make this explicit that y is equal to 0 at the ground. That seems like the easiest choice. And there are more interesting kinematics equations you can write for the y component because the velocity will be changing, so you can write the change of velocity equation and the v squared equation becomes interesting too. So keep those in mind, but for now I wrote the position equations since I'll probably be using them. Okay, then the second thing to remember for projectile motion problems is x and y motions occur at the same time. So what does that mean? The equations share t, the variable for time. So it's not just a coincidence or mistake that these are the same. They do represent the actual same time, and that'll be useful later on. Okay, let me number the equations and start out with the first question. What is the range? So range r is the horizontal distance. So I'll use equation 1. R is equal to v naught cosine theta, we're given all those, times, I need a time. So I'm looking at something specific here, time at this point in the motion. So I don't want to just label it with a simple letter t. I want to give it a little more description so that I don't confuse it with the general variable t. So I'll call it t subscript land because I'm looking at the time when the projectile is landing. Okay, so I need to figure out when this happens. And if you're just looking at the x component of motion, you'll never find it. X component of motion is very boring. It's just a constant speed of motion that's just going. So this is where it's important to remember that x and y motions occur at the same time. You can look at the vertical component of motion to see what information there is that you can use. And I hope as you look at this diagram that you realized when the ball lands, the y position is equal to 0. So that's the connection we are going to use. At time when the projectile lands, the y position is equal to 0. So let's write out that equation. So at the landing time t, the y position is equal to 0, and that's equal to minus 1/2 g t land squared plus v naught sine theta t land. So looking at the second equation, it's pretty simple. Solving it for t land, by the way, one factor of t land cancels out. It's because one of the times when y is equal to 0 is t is equal to 0 at the very beginning. So solving for t length, you get this. 2v0 sine theta over g. Let me label previous equation, equation 3. So plugging this into equation 3, we get the range right away. Let me write that down. Range is equal to 2v0 squared sine theta cosine theta divided by g. Now you can actually simplify this a little bit more. Let me leave that as exercise for you. You will need to use the trig identity double angle formula. Specifically, the sine double angle formula says sine of 2 theta is equal to 2 sine theta cosine theta. And you can actually derive this from the angle addition formula. And well, I'll remind you of those trig identities when they become more important later in the semester. All right, that's A. Let's answer part B. What is the maximum height? And there are different ways to approach this. I haven't used the v-squared formula in my lectures yet, so let me use that this time. You can also use the other approach. Okay, so the v-squared formula is let me write my version here off on the side as a reference. V final squared minus v initial squared is equal to 2 times acceleration times the displacement. Okay, so for part B, what's important is remembering that x and y motions are independent. Here, for the maximum height, the only thing that matters is the y component of motion. The horizontal component doesn't matter at all. So I'm going to ignore the horizontal component altogether for determining the maximum height and treat this like a one-dimensional kinematics problem involving the y component. So at the very top, the y component of velocity is 0. That's the point where it's neither moving up nor moving down. So that's my final velocity, 0 squared, minus the initial velocity, I'm looking at the y component, v naught sine theta squared, I'll just square independently, is equal to 2 times the acceleration. And you have to be careful with the direction here. The acceleration is downward, so I will say acceleration is minus g times the displacement. Again, careful with the direction. The displacement is upward, so I'll say it's plus the y max. All right, we have to solve this for y max, and it looks like it's pretty simple, so let me just do that. Y max is equal to v naught squared sine squared theta over 2g. The 2 minus signs canceled out, fortunately. Okay, now part C. What is the time at which the projectile lands? Oh, that looks like something that I solved for already. And this is one of the reasons to organize your work and keep good track of what you have been working on. Not only because that makes it easier for someone else to read, grade, understand it, because you might find that some of the intermittent result that you derived along the way to answering something is needed elsewhere again later. So keeping your work organized and neat helps you find that. So let me just copy that in my collection of answers. So the time asked for in part C is t length. So t is equal to 2v naught sine theta. That's all. These are the answers. Now, if these answers were all you are looking for, then it might look like I didn't gain anything. You could just look to them up in the textbook. Well, that could work for a standard problem like this one, where the ball is being fired from level ground, landing on level ground, and there's no surprises or any twists. But I started out saying that when someone introduces a little twist, knowing how to do this yourself gives you a lot of flexibility. So for example, imagine someone saying that instead of being launched from the ground level, the ball is being launched from some height, h. If all you memorize is the formula, then sorry, you're out of luck. There's no formula that handles that. But if you knew how to do this, then you can look through your equations and then see that in equation 2, we had that term for initial height. So instead of that being 0, now that's h. And with that change, you can work through the rest of the question. Or another change someone could introduce is, instead of wanting the ball to land at the level ground, someone could ask for a situation where the ball lands at some height higher up or lower down. Imagine the question asks, the ball lands at some height h above ground. And once again, if you are looking for a pre-derived formula, you won't find that. These variations are just too many. You want to have those formulas all pre-derived for you. But if you know how to do this entire problem yourself, then you can go through your derivations and realize what needs to change is instead of the landing height being 0, it should be the height h. And to tell you the truth, these modifications do make the problem harder. They make the algebra harder, and that's why I didn't do it. But they are doable. You just have to use some quadratic formula, or you might have to do it numerically, but they are doable. But only if you know how to set up these problems from scratch, from first principles. So you will get plenty of problem solving practice working through the homework problems. One last thing I wanted to emphasize, I think you might have some questions that are like this. There's a reason through this entire set I was using symbols and I didn't plug in any numbers. And that's because of the additional flexibility working through the algebra symbolically gives you. Some more difficult projectile questions will give you information in a kind of backward way. For example, instead of giving you the initial velocity and asking you for the final, which is very logical, easy to think sequentially, they might instead actually give you the final information. Maybe they give you final velocity, or they give you the range and height and ask you for the initial information. And if you are used to plugging in numbers at the very beginning and working through, how to do that backward can be challenging. But if your practice had been to work it out symbolically and then plug in numbers at the very end, then doing it backward is no more challenging than doing it forward, because all these equalities, they are bidirectional. They work forward and backward. But all that works only if you have them in symbolic form. So that's why I demonstrated this example using symbols only. And especially coming into Physics 4A, that might be a new practice for you, and I just want to recommend that to you as something worth practicing this entire semester. So this is the cart and the launcher setup for demonstrating the independence of the horizontal and vertical motion. This is the ball, and this is the coin used to trigger the launch manually. And here's the cart and the launcher itself. So let's see how this works. After putting the ball in, first we are going to trigger the launch manually using the coin while the cart is at rest. And the ball goes back into the launcher. Now we are going to trigger the launch while the cart is moving using the little metal piece mounted on the pole. And the ball still goes back into the launcher. Let's try that one more time. There you go. This is explained by separating the motion into horizontal and vertical components. When the ball leaves the launcher, it has the same horizontal velocity as the launcher. And as it undergoes the vertical motion up and down under gravitational acceleration, it continues to move at the same speed horizontally, so it ends back at the launcher. Now, I want to make this interesting by putting the launcher on an inclined plane. Watch what happens when we launch a ball while the launcher is at rest. That's what you would expect. The ball lands outside of the launcher. Now, what do you think will happen if we let the cart roll down? I'd like you to pause for a bit here and make a prediction first. Would you have predicted that? Let's try this again. This time with a bit shallower angle so that the cart has more time to roll down. I want you to think through this again while I get the track ready. Once again, let's test this by manually launching the ball with the launcher at rest. And the ball lands outside the launcher again. Now, give it another prediction. Where do you think the ball will land? Did you expect that? Let's give it just one more try. We are going to release the cart closer to the trigger so that it moves slower. So that's the demonstration. The challenge is, can you work this out analytically? It's an interesting challenge. The first time I saw it, it wasn't easy to answer. I think it's worthwhile for me to kind of go through it and do the explanation that some people were looking for. So the scenario, just so people are aware of the context, is it's coming from this demo. And with some of the demo videos, I don't explain things in full detail. I just put this as a challenge question, answer for yourself, and people keep telling me I want to know the answer. So I think I should do that. So let me do that. So I'm not gonna play the whole thing. I'll just skip to the part where I do the demo on the inclined plane. Yeah, this is the inclined plane, and just to make sure the things make sense, if I just oh, wait, did I? Yeah, and if I simply launch it from here, then it doesn't, it does the thing you would expect. The ball falls out because the incline fires the ball at an angle, so it falls out. Let me just go to the very last part where it's demonstrating. So now when you let the cart accelerate downward, so you are not launching it, or I guess I do that there. And then after that, I'm letting it, wait, I think I do it at least one more time. So when you let the cart slide down and do the other thing, the ball lands back in. And when I first heard this claim, I actually thought that's not going to happen that way, but I did a demo and it happened that way. So since we know experimentally how it should happen, there must be a theoretical explanation. So let's try to do that theoretical explanation. Let me call this way. Explanation for launcher on a cart on an inclined plane or track. So I'm starting from the assumption that people have seen the demo on a level plane, level track, and if the cart has some initial velocity, then as this thing triggers the launch mechanism and the ball is launched, because the ball launches with the inherited velocity and the vertical and the horizontal motion are independent, the ball, when it comes back down, it lands back in the cart. People have seen the demo, and that makes sense. Good. And when it's on an inclined plane, it's not often obvious to people that basically the exact same thing should happen. Um, so here's one way that I would, in search for a simple explanation, here's one way you could maybe try to explain it. So imagine, this is the track, and so you are going to have a cart moving on it with some, along the track speed as a function of time. And you are going to have a ball that is being launched, which is being launched with some initial speed that's perpendicular to the track. So if you are comparing with the exact vertical, then there's some slight bit of an angle there. And the vertical, as usual, is being defined by gravitational acceleration. Acceleration is in that direction, minus g. And when the train was perfectly level, we appealed to independence of the two perpendicular directions of motion. That vertical direction and horizontal direction, they are independent. That's why when the ball has vertical motion, doesn't matter, it still lands on the cart. So now when they are on an angle, the thing is, nothing stops you from appealing to that exact same reasoning. These two different directions of motion, this direction, let me call that x, and this perpendicular direction, let me call that y, they're still perpendicular to each other. They are, the motion along x and motion along y are still independent. The only thing that changes is, let me put it this way. So I think one way that allows you to kind of see this is, so you can take this and basically rotate it, rotate it, let's see, so that your track is in the horizontal looking thing. So I'm gonna rotate it so until, okay, my track looks horizontal. So, and my y direction that I drew before, it now looks vertical. This is like a change of reference frame kind of thing, perfectly valid mathematically. And once you've done that rotation, then what you're beginning to realize is, so the acceleration that was pointed straight down before, now it's tilted a little bit to the right. So it'll have component that's vertical, that's what's making the ball come down, and it'll have this tiny component that's to the right. That's what's making the cart accelerate. And here's the amazing thing. Moving under influence of gravity alone, these x and y components, well, the y component, it doesn't quite work on the cart because there's normal force supporting it, as we'll learn this week. But the x component, it's acting on the cart. And this same x component also acts on the cannonball, on the ball that's up in the air. So as far as their x component of motion goes, it's common to both the ball and the cart. And that's the only thing that matters to ensure that by the time the ball lands, the cart will be at the same position that the ball will be in. And again, because the y and the x direction of motion are independent of each other, and what makes them independent is really this 90-degree angle. Because they are independent, the fact that the ball has this acceleration doesn't matter. It just makes it come back down, and by the time it comes down, they have the same x position. So that's one way to answer this question, just conceptually, quickly. You do a change of reference frame, and if this argument makes sense, great, you're done. No more work needed. But sometimes people aren't satisfied with that. You want more work. So you can also do this mathematically. So the way you would do it mathematically is you would have an expression for describing position of these things. And I guess let me just to make this more painful for me. and use the straight axis. That way, I don't have to be concerned with any reference frame shenanigans. I'm just telling the horizontal as my x, vertical as my y. So what you can do is you can describe motion of the cart and the ball. I think describing motion of the cart will be easier. So I'm gonna just use the straight axis and not do anything fancy. I'm just gonna use the brute force method. I'm going to express the position of the cart and the ball and just work through the math. These conceptual tools, they are useful. They allow you to answer questions quickly, and that's really what physical intuition means. But it takes time process to develop that intuition. So that's why I'm going through the math right now. So for the cart, let's see. I know the magnitude of acceleration of the cart. I'm just going to use a formula that I happen to have memorized. You will learn how to derive this and next week. And this magnitude has to be broken into two parts. So if I imagine acceleration as being vector like this, it'll have this leg and it'll have this leg. So AY and AX. And this is still the same angle theta. So my AY will be this hypotenuse times sine theta. So it'll be G sine square theta. My X component will be G sine theta cosine theta. So this describes how the cart will be moving. And I think I can skip, because these are all both constant acceleration, I can skip to describing the position of the cart. Its x position will be 1/2 x acceleration, g sine theta cosine theta t squared, and I'm gonna the other two terms are both zero. Zero initial velocity, zero position. So I'll just leave them be, and the y position of the cart will be 1/2 g sine squared theta t squared. So these describe the cart. And with this, I have a mathematical tool to basically, at any given time, determine where the cart is. Let me do something similar for the ball. So for the ball, it's going to have initial velocity with the x and y components, and then it'll undergo projectile motion. So actually the acceleration of the ball, it'll only have y component minus g, because that's how the ball should go. Projectile motion, and the x component will be zero. The thing that I have to take care is that, let me draw it here first. So this is going to be my initial velocity vector. It'll have a vertical component and the horizontal component. So, and once you track the angles through, then this should be same angle as the theta as the angle of the track. So the vertical component will be vi cosine theta, and let me just call this v naught. And the horizontal component will be v naught sine theta. So with that, so my initial y component of velocity is v naught cosine theta. My initial component of initial x component of velocity is v naught sine theta. So with that, I think I have enough information to just write down the kinematics expression that expresses where the ball will be at some arbitrary time in the future. So that'll be position of the ball as the horizontal position of the ball as a function of time will be v naught sine theta t. Good. And its initial position is 0, and horizontally it doesn't accelerate. My y component the vertical position of the ball as a function of time will be minus 1/2 gt squared, the acceleration part, plus the initial velocity v naught cosine theta t, and initial y position is 0. So I have this set of equations, and to speak out loud like what I'm solving for. So at the time when the ball lands, that's the snapshot that I want to get at. The moment when the ball supposedly lands on the cart, they share the same x position and the same y position. Now, I don't want to assume the thing that I want to be proving. So let me just use this condition to say we are looking at when the y position of the cart will be equal to the y position of the ball. So that's going to be the starting place, and I'm going to be asking the question, will the x position of the cart be the same as the x position of the ball? If they are, then the ball will have successfully landed on the cart. So let me set up this equation first. I'm going to say the y position of the cart, 1/2 g sine squared theta t squared, t is unknown right now. That's equal to the y position of the ball minus 1/2 gt squared plus v naught cosine theta t. Okay, I'm sighing a sigh of relief, mainly because, I think I made a sign error. There should be minus sign here because the cart is moving downward. Let me put a minus sign here. I think I fixed the sign error. I'm still sighing a sigh of relief because every term has a factor of t, so I can cancel out a factor of t. And the remaining algebra I only have to solve for a linear. So I don't have to use any quadratic formula. That always makes things simpler. So I think I can just solve for t. Let me solve for t, and that'll be the tool that I need to figure out if this expression will be equal to this expression. So solving for t, in the interest of time, let me just do that in my head. Watch and see if there's any mistake. If there's mistake, let me know. So just doing it in my head, t is going to be equal to v naught cosine theta over 1/2 g 1 minus sine squared theta. Oh, I can simplify this a little bit. So let me simplify. 1 minus sine squared theta is cosine squared theta. So it's going to be v naught cosine theta. Let me move 2 over. I hate nested fractions. 2 times g cosine squared theta, and I can cancel out that 1 factor of cosine theta. So the time at which it lands will be t is equal to 2 v naught over g cosine theta. So let's just plug in this value of t into the expressions for the position and see if they are equal. Maybe they are equal, maybe they are not. I mean, I'm inclined to think they will be equal because the experiment shows they are. Let's plug it in and see. So the position of the cart at this moment in time is going to be 1/2 g sine theta cosine theta, and this thing squared, 2 v naught. Let me do the square and distribute them in so that I can cancel out some things. So 4 v naught squared divided by g squared cosine squared theta. Let me just do a bit of cancellations. One factor cancels out, one factor cancels out, and I can say that x of cart will be, and one factor cancels out, so it'll be 2 v naught squared sine theta over g. And I think all the units work out here. Yeah. So that's for the cart. Let's write out the position of the ball. That'll be v naught sine theta times this, 2 v naught over g cosine theta. Oh, wait. Made a mistake. There's this cosine there that I forgot to write out. Cosine theta. Okay. So with that, I think that's it. So I have 2 there. I have v naught squared. sine theta, g cosine theta. So this indeed is equal to the position of the cart. So this method took a little bit longer, but I guess the benefit of this approach is it the kind of the brute force mathematical approach. It eliminates a lot of what ifs. Because sometimes as you are making conceptual argument, it is possible to make a mistake, make an argument that's not valid. And in the brute force method, it's easier to check if you've made an algebra error. And I think I fixed all the errors I've made. So with that, so this is another way to show that even with the inclined track, by the time the ball lands, then the cart will be at the right position to take the ball. And if you are trying to find the reason how did that work, one might be that because the cart has moved downward a little bit, the ball had more time to move to the right. So even though, I don't know, that's one way to look at it. Yeah, I think in the end, this is a surprising scenario, and this is my explanation of it. Two approaches: one conceptual way to get at it with change of the reference frame, just imagine rotating it, and the other approach where you just work out the math. And when you work out the math, it turns out yes, what happens in reality is backed up by mathematics. So with that, let me start. So once I click start, it'll just start, and I'll have to watch my time. Okay, 6:08. Okay, that'll give me some idea. Oh, this is all right. I think this is a difficult question. I think, is it? Maybe well, let me just work through it. It says a cannonball of some mass is being fired from some cliff of some height. I think I might be scaring myself with the homework question. No, wait, it was the timed assessment question that was hard. Now, I do have a benefit of being very familiar with these questions, but even so, this is an especially long question, so I have to do quickly. Okay, it's being fired. They're not telling me initial velocity. Okay, let me keep going. The final velocity is measured. Okay, so the cannonball lands, and it's saying that final velocity is measured and found to be at an angle theta below the horizontal. In terms of this angle theta, what is the range of the cannon? There's a type of cannonball R. I think they're labeling ranges R. Give your answer in terms of theta, h, gravitational acceleration g, and any other physical constants needed. So yeah, this is a tough question because it's a backward question. One, I will tell you. So when you look at this statement, it should have you scratching your head because they didn't give you the initial velocity. Like if they gave you initial velocity, this would be a really easy question to answer. In fact, one of your homework questions was like that. And I think if I'm reading this carefully, they are not even letting me use the final velocity. They are letting me use the angle, but that's it. They want me to express my R in terms of theta, h, g, and any other constants. So not free final. So that makes this problem difficult because it's like citing alphabet backward. You have to know alphabet really well to be able to do it backward. So since I'm under the time limit, let me just work through this quickly without too much explanation. So I will just work on screen what that expression is for R. So I'm going to, I'm just going to write down some expressions that that might have something to do with this situation. So I know it's a projectile motion thing. So the x position is going to be relevant. And with the projectile motion, I know that's zero acceleration. So it's going to be just initial, or it's going to be the initial x component of velocity times the duration of time. And I guess this is going to be same as this. So let me just change the label here to say the v initial. That's my x component. And this equation has, so at the landing time here, let me call this t final. So I don't know t final, I'm just labeling it. And the distance it'll have traveled is range. And this is one of those questions that have 1, 2, 3 unknowns. So I haven't really made any progress, but I'm mapping out what I don't know and what I could maybe find out. I would like to find out this time at which it lands, and from my numerous practice with the projectile motion, I know usually vertical motion is helpful in finding the duration of time. So let me write it down. My y final, so when it's landing, let me just call that position 0. My y final, which I'll be labeling 0, is y initial plus the initial y velocity times duration of time, or the final time. And it's going to be plus 1/2 acceleration times time squared, but I know acceleration is downward at g. So let me say it's minus 1/2 g t final squared. Oh, and because it's been fired horizontally, my initial y velocity is 0. Oh, this makes the expression easier. Let me just, so I have a 0 is equal to the initial y height is h, h minus this term. So let me solve for t final. I'm just going to do that in my head in the interest of time. T final is equal to 2 times h over g square rooted. To get to this, I move this over and then solve for it on your time. I'm going to move on. So I can plug this in. And I remember doing this on video before. I think there's a recording of me doing this. And one of the things I will highlight there is that you really have a lack of information about your velocities. And one of the information that's given that I haven't used so far is this angle theta. So I'm hoping I can use that somehow. So I'm just going to write down some expressions that involve theta. So theta is the angle by which the final velocity is below the horizontal. So I could say tangent of theta is the absolute value of v final y over v final x. And I think I actually know the v final x because it's I've already labeled v final x because it's a projectile motion, whatever horizontal velocity there was, that's constant throughout. So I can actually relabel this as my v naught, one of the labeled quantities. So, okay, I need to have something about v final y. So I'm thinking through my kinematics equations. So I wrote down the one involving position. I haven't written down the one involving velocity. So that would be v final, would be v initial, and plus acceleration times duration of time, or in this case, minus g t final. And my initial y velocity was 0 for vertical component. So I think I know this numerator. Let me just sub in place. That's going to be g times t final. And for the time being, I'm not going to really worry about the signs. In the end, I will have theta be a positive quantity. So yeah. Okay, I feel like I might have all the information I need. So when you're solving questions like this, one of the things you should do is you should count your knowns, counter equations, or sorry, you should count your number of equations, and then make sure that your number of unknowns is exactly the same as the number of equations. So let me first start by counting my equations. I have 1. This was the very first equation I wrote. I have I solved this, so I'm gonna label this as 2. It's the same thing as what I started out with. And this is my equation 3. And let's count my unknowns. I had a 3 to start. And this is not a new unknown, so everything is here is known. And everything here is already labeled, like V naught. And so I have 3 equations, 3 unknowns. I should be able to solve it. So let me do that. I think the most natural way to do this is I can use equation 2 to eliminate T final from every other expression. So that will give me 1 prime to be, so I'm solving, plugging in this into 1. So R is equal to V naught times square root of 2H over G. Let me plug T final into 3. So 3 prime is becomes tangent of theta equals, I guess there's a factor of G here. Let me write it out first and then do simplification. G over V naught square rooted 2H over G. I can think of this as a G squared square rooted, at least if I'm not worried about signs. So with that, I can say it's a 1 factor of G here cancels out 1 factor here. So square root of 2HG over V naught is equal to tangent theta. Okay, I can solve this equation for V naught and plug that into my first equation to get an expression for R entirely in terms of these quantities. So solving that for V naught, I get square root of 2HG over tangent theta. Plugging that into there, I get, so 1 prime, R is equal to square root of 2HG over tangent theta times square root of 2H over G. And yeah, I think I remember this simplification. G's cancel. Doesn't matter what planet you are on. And square root of 2H times the square root of 2H gives me just 2H. So the final answer here is 2H over tangent theta. All right. Wow, that took me 10 minutes, which is a little bit too much. But so, here I was explaining because I can't stop myself. But, when you're solving through this, I do want you to manage your time well and not be down this too much on just part A. So let me write down. R is equal to 2H over tangent theta. And that's really the answer. Let me okay, if the angle theta is found to be equal to 45 degrees, what is the initial speed of V naught? Oh, I think I've done that before. So V naught in terms of H, okay, so I have that V naught is equal to, so V naught is equal to square root of 2 times H times G and divide by tangent theta. That's where, if it's 45 degrees, tangent theta is 1. I don't need that. Yeah, and the rest are in terms of the variables I'm allowed to use. If the initial speed of the canvas by firing at some angle above the, oh yeah, that's gonna take another long. Yeah, I think it's fine. So find an expression for the range R given an initial speed and the launch angle above the horizontal. Yeah. Let's see. Can I do? Oh, I can answer D first. So how does the launch angle theta not compare to 45 degrees? It should be less than 45 degrees for launch angle because of the initial height h. Landing angle bigger than 45 degree? Don't know. So this is my educated guess, and I'm putting that in first because I recognize I have 7 minutes left, and I want to make sure if I run out of time while solving C, I get some kind of response in for D. So let me try to do parse C again as quickly as I can. And I think the two things kind of balance out, which is that, let me actually take a screenshot of this. two things balance out, which is that so the way I'm doing this, it actually does take longer than if I were working this out on paper without attempting to explain it to anyone else. So so there's that aspect, but at the same time, I know these questions much better than most people in the class because I've done them a dozen times. So I think those two things balance each other out. Let me just put that on the side. That's for later. So let me just quickly work this out. I got what? Well, about 5 minutes. So I gotta scroll down so that I can write. So the situation that the question described was very different, or it was slightly modified. As in, I had H and I had a ball that was being launched with some initial speed of v naught at some angle theta. So this is the more typical projectile motion question, where you are given the initial parameters and then you are asked for what is the range R. And I hope this feels familiar to a lot of people, so you can write it out quickly. R is equal to the x component of velocity, v naught cosine theta, times t final. So I need the time information from the vertical motion. So there I will write out the y position, the y final, which will be 0 when it lands. That's where I'm labeling y is equal to 0. That'll be initial y height, h. Plus this time you do have initial y velocity. So plus v naught sine theta, the y component of velocity. That's really, this is broken into two parts, v naught cosine theta and v naught sine theta, times t final, minus 1/2 g t final squared. And yeah, so this is the thing that's gonna be challenging, because nothing here really simplifies the way it did when this was equal to 0. It's not, so you just have to use quadratic formula. So using the quadratic formula, you would say, all right, so this is my A, this is my B, this is my C in the standard form. So I have my T final is equal to my minus B, so minus v naught sine theta, plus minus square root of b squared, so v naught squared sine squared theta, minus 4ac, so minus times this, so that's going to be plus 2g, and then c, so that's 8. Sorry, I'm this. I'm not trying to really explain all that well because I'm under time limit, 4 minutes. Okay, so that's numerator and divided by 2a. So it's going to be minus 1/2 cancels, so minus g. So minus is cancel, and in the context where it matters, this should be minus plus. And you can actually go this far. By examining this, you can see that when you have minus here, time will be negative, and you don't want that. That represents this time here, which didn't really physically happen for us. So I just want to retain the positive sign here. So with that, my t final is equal to v naught sine theta. Let me split it over g plus, and then I have all of this. Square root of v naught squared sine squared theta plus 2gh divided by g. All right, so plug that in there. That gets you the R. Let me just type that in. I don't think it really simplifies from there anyway. So I'm just going to type that in so that I can get an answer in within the time limit. The expression for range is v naught times cosine theta times, and then all of that in. So v naught times sine theta divided by g plus square root of v naught squared sine squared theta plus 2gh divided by g. I think that's it. And don't worry so much about typos and whatnot. This is all manually graded. So when I submit an end, it won't uh, it won't give me a score because these are just basically essay questions. A human grader has to look at it, and so I have to look at it and manually grade it. And I do want you to note how sparse information I put in into these answer boxes. And I think that's the best thing to do. And put your work into the add work thing. And if you have time remaining, you can do that during this time. Oh, you know what? I think I have time. Yeah, let me enter it now. I mean, you don't have to, but hey, if you have time, then why not? So okay. Um, so in my case, it was and this portion was slightly quicker just because I had already worked it on a computer. But most people, I do recommend you working on paper, so you will need time to scan in and all that. So let me just put in my work for now, and then paste it, and then paste that, and then I will submit an end. And and it'll actually, after having done that, it'll give you an wait, save a work and continue. Oh, I see. Save this work and continue. So yeah, after you submit it, it'll actually, on the immediate next screen, it'll give you an opportunity to edit this as well, which is fine. If you are ready to do that, then you can. Now, suppose you didn't use that opportunity, then you can see this. I'm gonna refresh this screen, and you will see that it still gives you opportunity to add or attach work, or edit the work that you attached previously. Um, so, so yeah, that's I guess the full demonstration of this thing.